In this video, we'll be using the rules of inference to prove arguments such as these. And as you can tell, they get a little more complicated as we go from left to right. There's going to be a bunch of these in this video. Now, if you don't know what the rules of inference are, I actually made a video on the rules of inference explaining some of the nuances behind how to use the rules. Link will be down in the description for that. It is called Introduction to Rules of Inference. But if you already know what you're doing with that, let's go ahead and practice some of these problems. So for this first problem, we're going to prove this statement right here. So when you start off a proof, you always want to write down number 1 first. And what's the goal of the proof? Well, the goal is to use the rules of inference, or the laws of propositional logic, in order to get to the conclusion. So with these two hypotheses, you need to be able to manipulate these guys somehow in order to get Q. So first things first, I'm going to write down P or Q, right? And since this is one of the hypotheses, we can write down given as the reason. So for every step in your proof, you must write down the reason why you use, how you got to that point. And, well, P or Q is given, right? It's one of the hypotheses, so we can write down given. You can also write down hypothesis for this reason. These are both accepted. But I like to write down given because given has less letters. Sorry, it's all one word, okay? But given has less letters, less to write. I'm very lazy. But number 2, what are we going to do next? Well, remember, you have to use the rules of inference to get to point Q. You could write not P here and write down given. You know, write down all the givens first. But sometimes your hypothesis isn't used. Okay, you don't have to always use all hypotheses. So I'm not going to write it down until I have to use it. All right, next thing, we can kind of look at the structure of this. What's going on? All right, well, what I got is that the conclusion is Q. The conclusion in this case is Q, and we have a Q right over here. Well, how do we get from this guy to this? Well, one thing that sticks out to me is modus ponens. Modus ponens. So we're going to try to get to this point right here. And remember, modus ponens is A dash B, A over just B. This right here is modus ponens. So we could try to get to this point. And the reason why I thought of this was because, remember, the conditional identity allows you to turn a statement with or in it into a conditional. So we can actually apply the conditional identity onto line number 1. So whenever you use a reason but other than given, you need to write down the line number that you actually applied the statement to. So conditional identity 1. And 1 is right here, so we apply the conditional identity to this guy. So the conditional identity gives us not P dash Q. Well, now we can use not P, and I'll show you why. This will become very apparent in the next step. The reason why I wrote down not P now in the given, right, is because this takes the form of modus ponens. Modus ponens has an A here and an A here. Well, A is just an entire statement. A can be a negated P, A can be a P or Q, A can be anything. A is just a section of your statement. It could be an entire propositional, a compound proposition, okay? But in this case, it is just not P. So not P right here can be treated as A using modus ponens, all right? And Q can be treated as B. Well, here's the thing. We have the structure to use modus ponens. We have not P and not P, which is A. We have A's in this case for modus ponens, and we have Q here. So what can we do? Well, we can apply modus ponens to lines 2 and 3, right? And look at modus ponens. It simplifies to the guy on the right side of this arrow, which is B. And remember, B in this case is Q. So we can write down Q here. So at the very end of your proof, you should have the same thing as the conclusion as what you wanted to prove using your arguments. So keep in mind, you use the hypotheses given inside of your argument, and you use the rules of inference and the laws of propositional logic and manipulate this in order to get to the end point, like so. The next problem will look like this. So we want to prove R based off of these arguments right here. So let's write down P dash Q first and Q dash R. And the reason why I'm writing these two down first is because right here we have P dash Q and Q dash R. Off the bat, that looks like what? That looks like hypothetical syllogism. And the reason why, this is how I memorize hypothetical syllogism. I talked about this in the introductions to rules of inference, but we have P dash Q and we have Q dash R. And we can actually kind of see P goes to Q and then Q goes to R, so we can kind of connect it inside of a line and remove the middleman to get P dash R. I'm not certain if this is the actual way that people have developed that proof, but that's how I memorize it. That's how I remember it. And hypothetical syllogism becomes very apparent once you start seeing it like that. But let's write down hypothetical syllogism. I don't have enough space to write down the entire thing because I'm writing with a very big pen font. So hypothetical syllogism, and we're applying this to lines 1 and 2, right? Hypothetical syllogism needs two statements, so 1 and 2, and we end up getting P dash R. So using hypothetical syllogism on 1 and 2, we get P dash R, right? P dash Q, Q dash R, and we can kind of connect the arrows to get P dash Q and dash R, and remove the middleman to get P dash R. That's how I remember it. That's how I remember it. But now we have P dash R, and since we have P dash R now, I'm going to write down P and write down given. And the reason why I chose P next is because this looks like the structure of modus ponens again. So we can actually write down modus ponens, right? And apply modus ponens to 3 and 4. And by using modus ponens, we get the final answer, R. And R is the same as the conclusion in our original argument. Let's take a look at this problem, and this one looks a little bigger, and there's actually a couple paths you can take with this problem. You don't have to follow the exact path I showed you. If you still get to the right answer, then it's the right answer, of course, but this path I'm going to show you is going to be the one that I think is the most simple, the easiest one to follow. So let's go ahead and write down P or R, and this is of course a given. Oh, my laundry's done. And number 2, we're going to write down the conditional identity of this. Well, why am I going to do that? Well, the reason why I want to do that is because we have an R dash S here. And if we end our condition with R, then we can combine these two guys right here. And you'll see what I mean by this if that was confusing. So let's write down P dash S with conditional identity. And for number 3, we can write down R dash S. Wait, sorry, not P dash S. What am I saying? This is P dash R. Brah! And R dash S. Okay, and this is a given. So we have that now. And then, remember, we can kind of connect the arrows, right? Bad way to put it, but we have P dash R, and we can turn this into P, not P dash S, using hypothetical syllogism. Hypothetical syllogism. And this right here is, remember, put the lines. Don't forget that because your teacher will take away points. So 2 and 3, we get not P dash S after, connecting these R's together. Number 5, and let's write that a little closer. So now we have not P dash S. Let's go ahead and write down P dash Q. Well, why are we doing this? Well, one way that I saw wanted to go about this was, remember, the endpoint is Q or S. And we only have conditionals right now, right? Well, there is one rule of inference that can give you an OR operator at the end, and that one is resolution. So we should try to get to a point where we can use resolution. All right, and what's the format for resolution? Resolution. Well, right now we have 2 conditionals, and the format for resolution looks something like this. We have A, let's write that in the, where do I have space? Let's go ahead and make a section off like this, and then write resolution with red. So we have A or B. We have not A, not C, and our final conclusion is B or C, right? So this right here is resolution, and look at this, not P and not and P, well, this kind of looks like resolution already, right? Remember, resolution needs a not A and a regular A. We have a not P here, and we have a P. These two are already negated, and we have two different guys, and these can actually be the same, but we have two different guys here. So we have B and C, and we have S and Q. Well, this looks an awful lot like resolution. So how do we get to resolution? By using, very convenient, the conditional identity. The conditional identity turns the conditions into OR statements. So let's use the conditional identity. And I might have to cram this a little bit. But conditional identity. Conditional identity. This is kind of scaring me a little bit, because when I shorten identity, it looks a lot like my actual name. But let's write down conditional identity for 4 and conditional identity for 5 here, right? So with the conditional identity for 4, we get P or S. And conditional identity for 5, we get not P or Q. Now, keep in mind, for this conditional identity, you might be wondering where the negation went. The negation just got negated again. So the conditional identity puts a negation on the P again. They get canceled out. All right. So we get P or S, and we get not P or Q. Oh, oops. There's an underline still there. And now, well, we have the format for resolution. And why I thought of resolution was because resolution has the OR in the format, and we have the Q and the S right next to each other that we can use for resolution to get Q or S. So right now, if we use resolution, the rule of inference resolution, on 6, 7, we get S or Q. All right. Remember, in this case, A is P, not A is not P, and B is S, and C is Q. So C gets put on the right side of the OR, and B gets put on the left side of the OR, right? Here's the thing about this: it doesn't matter which side you put this, left or right. Commutative law states that Q or S, S or Q and Q or S are the same exact things, right? So if I had space, I would put Q or S here. But Q or S is the result that we are looking for. This right here is the next problem, and I'm not gonna lie, my thumb hurts a lot right now. So I mentioned this sometimes in videos, like once every, like, I don't know, 50 videos I've mentioned this, but I like powerlifting. I've been powerlifting for like 4 years. If you don't know what powerlifting is, it's strength-based lifting, squat, bench, deadlift, and in powerlifting you use something called hook grip, okay? And when you're deadlifting, your thumb wraps around the bar and you put all the weight onto your thumb. And the reason why you do that is because you actually lose grip at the higher weights. So my thumb, I just deadlifted just now. My thumb hurts like a good bit. I don't know. Oh, it's like bruised. It like hurts. And when you're writing, you know, your thumb is pressing down on the pencil. So my thumb hurts while I'm writing. But I bear with it because oh my god, I just choked on my saliva. I bear with it because I like making videos. I'm smiling right now. I don't have a webcam, but I'm smiling right now looking at you guys. But let's go ahead and write down this first thing right here, and I'm gonna write down P and not Q. All right, why am I doing this? Why am I writing down P and not Q? Why is that the first thing that comes to mind? Well, when you look at this problem, might not be initially clear, but we kind of have the format. We kind of have a format for modus tollens. So I haven't shown you that in this video yet, and I'm trying to cover all the rules of inference. But we have the format for modus tollens, and modus tollens looks something like this: dash P, not B, over not A. Now, why do I want modus tollens? Why do I want to do that? Well, we have an R here, and R is what you're actually going to apply to modus tollens. Okay. Oh, sorry, not Q. This is not Q. This is not A. So R, we want this to be not R, but we don't have a not R here. So how do we get to not R? Well, we could have used the conditional identity, but you will find out that that isn't very effective because we have the AND operator here, and we can't do anything with AND and OR. So we have modus tollens here, and I'll actually show you. Okay, next thing, I'm going to use simplification. So I haven't shown you this in this video yet, but simplification on line 1 to get not Q, right? And so right on the third step, R dash Q with given. here's the thing. Now we have the format for modus tollens. Modus tollens has the format of A dash B, and in this case, R is A and B is Q, right? And it's perfect. Not B, not Q, right? So we can use modus tollens. So let's go ahead and use modus tollens on this. Modus tollens on lines 2 and 3. And remember, modus tollens gives back the result of not A, and in this case, R is A, right? So we should get not R for modus tollens. All right, well, for modus tollens, we got not R, and that's exactly what we wanted, right? We have a not R in the conclusion, and we're getting one step closer to the conclusion, right? Along the way, you should be, slowly building to the conclusion, and we have a not R now. All right, let's write down one last thing. We have not R. Where are we going to get the P from? Well, we only have P in one statement. Well, P can be simplified from line 1. Oops, did not mean to do that. Simplification on line 1. And we get P. Because when you have two guys separated by the AND operator, you can split them apart. You can just take into account only one, and that's because of simplification. So we actually, first we use simplification on line 1 to get not Q. Then we use simplification on line 1 again to get P. Why does this work? I thought that laws of propositional logic removed the previous statements. Remember, your laws of propositional logic, when you were simplifying an equation, they remove everything. Okay, you can't go back a step and then take what you had in the steps before, but for rules of inference, you can. Remember, when you apply the rules of inference, things aren't destroyed. Okay, this P and not Q isn't destroyed once we apply simplification on it. We can use simplification on line 1 again to get the P. So remember, when you use the rules of inference, unlike the laws of propositional logic, previous things can still be used. They aren't, removed. All right. But now we have not R and P. We have not R and P. We have the individual components of this. How do we combine them together? By conjunction. That's another one. Conjunction. So conjunction, very useful. Conjunction and simplification are very useful. I highly suggest you get familiar with these. Simplification isn't really that bad to understand. Just keep in mind, if you have anything separated by an and, you can just split them apart, right? That's simplification. But conjunction, you can combine things together. So let's combine 4 and 5, both with the AND operator, not R and P, and we actually get our answer. Little warning, again, simplification is very important. I'm going to repeat that, because simplification, I use that probably the most in this class. Besides like modus ponens and modus tollens. They use modus ponens and modus tollens a lot, and hypothetical syllogism. But simplification, man, it makes your life way, way easier. And it's one of the only rules of inference that allows you to mess around with the AND operator. All right? So simplification, give it some love, give it some spirit, and kiss it on the cheek or something like that. But you're going to be using a simplification a lot. Let's go ahead and stop talking. I'll move on to the next problem. You're already telling me to shut up. I get it. Let's take a look at this one final problem, because I think the video is getting too long, and I know that people won't want to click on a 30-minute video. So let's take a look at this. It's a little more chunky. Looks a little more chunky, but we have the P or Q here and P or Q here grouped together. So we can already imagine. I feel like you can already imagine that you're going to use these laws together. You're going to treat P or Q as a single statement. And I'll show you what I mean by that as I work through this problem. But let's go ahead and write down not P or Q first, dash S, and S dash T first. Now, why am I doing these two first? Well, remember, the arrows connect. We have an S at the conclusion here. We have an S at the condition here. So remember, this is hypothetical syllogism, dash S, and dash T. S is connected to T. P or Q not is connected to S. We can connect them all together to get P or Q dash T. So this right here is hypothetical syllogism. Hypothetical syllogism. And I don't have enough space to write down the numbers. Numbers 1 and 2. All right, next thing. What do we have? What do we have? What do we have? Well, let's write down P or Q dash R. And this right here is given. It's one of the hypotheses in the argument that we're trying to prove. Why did I do that? Why did I do that? Well, here's the thing. Resolution. Resolution. Well, why am I using resolution? Well, remember, conditionals can be expressed as the OR operator. And we have an R here and we have a T here. So how do we, combine R and T with two conditionals? We can use resolution. And we can actually turn both of these conditionals into an OR operation. So let's actually turn both of these conditionals into an OR operation to use resolution. So let's go ahead and do P or Q dash T and not P or Q dash R, and both of these are conditional identity. I'm actually going to copy and paste this so I don't have to write it again. And this right here is the conditional identity on 3. This right here is conditional identity on line 4. So where does resolution come in? Oh, oops. Oof. Wait. Big mistake. Big mistake. Big mistake. Big mistake. Conditional identity. There you go. I forgot to turn the arrows into ORs. But where does resolution come in? Well, now that we have this, how do we use resolution? Let's look at the structure of resolution real quick. The structure of resolution has A or B and not A or C. And this simplifies to B or C, correct? This is resolution. Well, we have that format here. It might not seem obvious that we have this format, but remember what I said about these rules of inference? These rules of inference, the variables, can be entire compound propositions. They can be entire compound propositions. So A right here is P or Q. And we have not A here, which is not P or Q. Isn't this the same structure as resolution? Right? We have A and not A, and we have P or Q and not P or Q. This is the same exact structure. And we have a B and we have a C here. And in this case, B will be treated as T in the resolution, and C will be treated as R in the resolution. So when you use resolution, what's the final result? B or C. Resolution. So let's use resolution on 5 and 6. Right? And we get B or C. So we get T or R. Okay? We're getting one step closer to this guy right here. We're getting pretty gosh darn close to this guy. But remember, this is a condition. This is the OR operator. Now here's the thing. Remember, the OR operator is just another way to write down the condition. So we can actually flip around. We can flip around R and T because R is on the left here and T is on the right. So we want R to be on the left and T to be on the right. So let's use commutative law on line 7. And finally, we can use the conditional identity to get not R dash T. Conditional identity on number 8. And there it is. There is the proof in its full form. Now, I think there might have actually been an easier way to do this. I'm not certain. And my intuition is telling me there is. If you guys find an easier way to do this, actually, how are you going to write that down all in the comment section? I was going to say write it down in the comment section, but there's no way you can write it all. But yeah, this is the end of the video. If you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Also, one last thing. The trigonometric... Okay, I don't know. You guys are probably going to watch this very far off because right now I only have like 400 something subscribers. Also, thank you for 400 subscribers. I hit 400 subscribers. I never thought I would hit 400. I thought I would only hit like 100 like a year ago. But that's amazing. I'm glad you guys like watching these videos, especially to the end. And I'm just talking to myself right now with an empty room and a fan blowing into my face because the room's hot right now. But yes, dude, the trigonometric identities video, trig integrals, it has like 2,000 something views. What? I never thought I would get 2,000 views on something. I'm high-key kind of happy. I'm really happy about that. So I really thank you guys. Even if you haven't seen that video, I'm very happy about that. Also, I think my how to count in binary video is getting close to 1,000 too. So Who knows? Who knows? I put comments under those like I was excited. Imagine the binary video stops at 999 views, and I just end up looking like an idiot because I put down the comment on the video. You can actually look at the video right now. It's in my computer science playlist. But I put the comment, no way this is going to hit 1K views too. If it doesn't hit 1K views, I'm going to look like a dumbass. But that's the end of the video. Thanks for watching.